I were, last chapter, or I should say last section of chapter 2.5 of chapter 2, if I was to give you this function and say, hey, find dy dx, you're like, do it. Okay. But where would you start? What do you think? Get y alone. Sounds good. Get y alone and find your derivative. Go. Get y alone and find your derivative. We'll talk in just a second as to why getting y alone is a good idea. Oh, yes. I think the handout on Friday was weird. It was supposed to come period 6, it came period 5. I was all confused. Plus extra if you didn't get your spiffy personal edition of Heritage Headlines. Has Spirit Day, all sorts of stuff. You can grab one on your way out. Okay.
Like, honestly, who would have guessed that?
I know, it's so sad.
Are you guys found it?
I didn't know Harambe existed.
I didn't know it had anything to do with Moscow.
I saw the video. They're basically.
Okay. Solving for y. What do you get? Right? Have you found a derivative, right? Or are you just like shooting the breeze and not doing anything?
You need to simplify it. Get the x on the top.
Put 10 over x minus 3.
Yeah, you can do that.
So there's a way to rewrite it?
Yeah.
Take a derivative of one of them. If you have not yet. Take a derivative of one of them. And I'm going to start in just a second. Take a derivative both ways.
Now you need to move that.
This way, I would rewrite first, right? This way, we would need the quotient rule, yeah?
Oh, that's so
Oh, either way works out. On the left, it would be bottom view top. Don't we only say dy dx if it's in y? Okay. dy dx equals bottom view top, which would be 10 times negative 3, right? Minus top d bottom all over bottom squared. We need to simplify some stuff, which would be negative 3x minus 10 plus 3x, unlike people that keep throwing their poor little seals. Distribute that negative. What happens to 3x's? What do you have left? Negative, I heard a couple of you. You just know negative 10 over x squared. Does it work on the other side? Because all you have to do is write dy dx, right? Equals negative 10 x to the negative 2. Derivative of any constant is. And then I rewrite, right? Negative 10. What was the key to solving it from the get-go? Solving for y, getting y alone, right? Why do we have to get y alone? Why do we write dy dx? We'll get back to those questions in just a second, but first of all, dilemma. What if mixed up functions are much more difficult? What if mixed up functions are much more difficult? Now in this one, we ended up with a pretty nice derivative, meaning we were able to divide both sides, or I should say both terms in the numerator by x. And the derivative could have been pretty easy, but the quotient rule, that's not very fun. In some functions, let me show you a quick example. Don't write it down. Just check it out. Get y by itself. Y is in how many places? Can I combine them somehow? Why can't I combine them? They're not like terms, are they? Okay, so I can't combine them. They're not like terms. Can I factor out a y? Oh, I could. Couldn't I move the 5x that way? And then And couldn't I take a y out?
Yeah.
But what's still stuck? So am I in some trouble? Can I get y on? Maybe try to complete the square. Nobody wants to do that, right? And this one is not even possible because we have a 3xy, it's messed up. So, if we were stuck with every time get y alone, we'd be in some deep trouble with more mixed up functions with x's and y's put together. So there has to be another way, and there is. There is another way of looking at it. But first, before we get to that other way, I want to get back to that question I asked just a second ago. Why dy dx? When we have something super easy, like y equals x squared, let's not do that. Let's do 2x plus 1 to the 6th. We can practice what rule?
The U1.
Chain rule. The funny one, u prime. Okay. If I said find the derivative, if I said find dy dx, what do we write? Very first thing, if there's no rewriting involved. What's the very first thing we write as we go to find the derivative? Dy dx, but why? To make sure we're deriving. Show we're deriving. Stands for the derivative, we've learned that. Why can't we just rewrite it? Why does the y just magically turn into a dy dx? Let's go to the other side. How do we derive 2x plus 1 to the 6th power? Write 2x plus 1 6 times and do lots of multiplication. Then use a power rule. What are we going to do? Bring the 6 down. Keep the inside the same. Derivative of the outside, bring the 6, make it a 5, keep the inside the same, times u prime, which is? Why is that times 2 necessary? It's the inside prime, right? The inside prime. Guess why we write dy dx? Because it's y prime. And if I bring down the 1, and look at y as a variable, similar to how I look at x, I could say the derivative of y, bring down the 1, take away a power, it'd be 1 times y prime. And who's y prime? Dy dx. I'm really doing a little baby chain rule. Every time I write the derivative of y is dy dx. I'm really doing a chain rule. Bring down the 1, subtract a power, just 1 times y prime times dy dx. So if I get something like this instead, the function that we saw at the very beginning. Let's say we didn't get y alone, even though we could on this one. Let's say it was stuck, like one of those nasty ones that we'll see soon. How would we find dy dx? We couldn't write dy dx right away. Why? There's not a y alone whose derivative is just y prime, or dy dx. So we can't write that right away. We can't say that dy dx equals because y is not alone. But what we can do is take our function xy plus 3x equals 10. And we can do the verb instead of the noun and say, well, we don't exactly know who dy dx is yet. But I'm going to derive, because that's what I'm supposed to do, because that's how dy dx comes about, is by deriving. We take the derivative of it as is. We take the derivative of it without rearranging. Now, how do we do that? Well, let's start right to left. That's the easy way. On the right, what's the derivative of 10? Okay, move your way, work your way to the left, across the equals. What's the derivative of 3x? 3. Hold on. The derivative of 3x is 3. Why? Bring down the 1. 3 times 1 is 3. X to the 0 power. times x prime. What's x prime? 1. You could technically say every time we take the derivative of something with respect to x, we're doing chain rule also, but it's always times 1, so it's not a big deal. Let's keep moving our way to the left. Question. X times y. What rule do I need whenever there's a times? And I have a first and I have a second, right? Okay. How does product rule work? Second, just rewrite it. D first. What's the derivative of x? 1. Plus first x. What's D second? dy dx, or y prime. Wait. Second, just rewrite the y. Nothing's going on. D first, derivative of x is 1, plus first, rewrite the x. D second. Hey, wait a minute. Who's the derivative of y? dy dx. We've always said the derivative of y is dy dx. Is anybody else confused? It's just like a prime. I apologize. That was meant to be a 1. Did it look like a prime? Maybe we should erase it. It looked like a prime to me after I looked at it again. But who's the derivative of y? Who's y prime? dy dx. Well, but our job isn't to find this nasty expression, even though this is a step in the process. What's our job to find? So if you can't get y alone, see if you can derive and then get dy dx alone. Can we do that? Yeah. How do we get dy dx alone? So, well, yeah, we can make it look prettier. So that would be y plus x dy dx plus 3 equals 0. You guys are saying subtract with 3. I like it. Is there anybody else we should subtract? So we'll leave the x dy dx. And we get negative 3 minus y. Oh well, for right now it's okay. Subtract the 3, subtract the y. How do we get dy dx alone? Divide by x. And we end up with dy dx is equal to negative 3 minus y all over x. Now, what's weird about that derivative? Go back to the first one that we did right underneath the title. Does that match the same answer? No. But why? The first answer is only in terms of what variable? Go check it out. Only in terms of x. This one is in terms of who? X and y. Guess what? The first derivative was what we call explicit, only with x's. And the answer, this one is called implicit because it has y's and x's. It's hard to see exactly what's going on. But if I could, which is not always possible, with the nasty, more difficult ones, we couldn't get y by itself, so we would stop and say that's the best we can do. But with this one, since we could get y alone, and we did, we got, what did we get? 10 minus 3x over x, and we did some simplifying. Technically, if I was to use that fact, which we could do in this one since it was easy, we could double check and make sure we were right, because we could say negative 3 minus 10 minus 3x all over x, which I know some of you guys are like, oh, it's disgusting. I know, I'm just trying to show you it's the same thing in essence, though. We would go ahead and simplify, multiplying top and bottom by x. Just trying to prove a point real quick. The x would distribute in. We would get negative 3x minus 10 minus 3x, because the x's cancel on the second term. On the bottom, I get x squared. And this should look kind of familiar, because to be honest, this is exactly what we got when we did quotient rule. It's just another form of the same thing. It's just looking a little different because we had x's and y's all mixed together. Now guys, last year there was something that we learned where we kept x's and y's all mixed together and we didn't like getting y by itself. Does anybody remember when we liked having y's in the midst of the equation and not alone? equation of a circle. X minus h quantity squared plus y minus k quantity squared equals r squared. Y was stuffed. Where else? Ellipses, conic sections, hyperbolas, even parabolas in vertex form. Well, we can kind of make an argument either way. But when we were doing like directrices and foci and all that weird stuff, we had y's like all mixed in. But that was only y squareds. It get a little bit worse, but long story short, last year there were times that the equation clue form was best when the y was not alone. When it was all mixed in, and even to get it alone, they were like nasty plus or minus square roots, and it was disgusting. So similar to last year, there are times the derivative is best left in terms of x's and y's. Now, let's keep going. I solved an example, but we still haven't written down exactly what I did, how I did, why I did. So, let's first of all review real quick the difference between explicit formulas and implicit formulas. Explicit, in general, is in terms of one variable. I'm just going to say one bar. You know what bar is, right? Y bars? Bar is variable. In terms of one bar, or solved for one bar, we can say something else to the effect of not the independent, lo siento, the dependent bar. The dependent bar has been solved for, aka y is isolated, aka y is by itself, y equals. But we saw that y isn't the only thing that could be by itself. V could be by itself for velocity. S could be by itself for position. So I'm just trying to say, whoever the dependent one is by, or is for a problem is solved for, is isolated. Implicit, the equation is going to look in terms of multiple bars. So you're going to have x's and y's together. You might have like a's and b's. I shouldn't say that. Those are usually constants. Could have v's and r's and h's all mixed in. Just multiple bars are in there. They're all mixed up. We could think of it as mixed up or non-isolated. So then for examples, well, you guys have already seen them, but just for the sake of showing you explicit formulas, you could say y equals mx plus b. Right? Isolated. That's an explicit formula. But technically, if I were to do y minus y1 equals m times x minus x1, isn't that technically implicit? Y is not by itself. Y minus y1. It's technically implicit, just usually we go ahead and solve for y at the end. Difference between explicit and implicit. Explicit, we could use something to the effect of y equals plus or minus square root of x minus h quantity squared plus k. Implicit, we could say x minus h quantity squared plus y minus k quantity squared equals r squared. Hold on. I did a bad job. I should have written the implicit one first. It would be r squared minus x minus h squared plus or minus square rooted plus k. Ugh, it's even worse than we thought. On the left, it's the implicit form, which we did not use last year. That's just disgusting. But on the right, oh hey, complete the square a little bit. You have a nice form of the circle. You can see the center, you can see the radius. And the list goes on from there. In explicit formulas, there's ones where y is by itself. Implicit formulas is where basically the y is mixed in somehow. How do we explicitly derive? Derivative of the left, derivative of the right. But every time we do derivative of the left, since we're just taking the derivative of y, we just got to write dy dx. No big deal. Just worry about the right-hand side. But now if it can be all mixed up, we got to kind of worry about everybody. So to worry about them, here's our new method. And it's not exactly new. You just might not have fully understood what we were doing the whole time. Every time we wrote dy dx, we were saying y prime. The derivative of y is 1, but we still need times the derivative of the inside. Don't worry, you'll see more what I mean as we do some more examples. Implicit differentiation. Kind of a different thought process. It's not really a new method. It just takes a little more pondering. It's a good word. Steps. Differentiate both sides. What? We always kind of did, just we didn't really have to think about it. We just wrote dy dx. When you have a mixed up equation, you're going to have to take that implicit equation you're going to take ddx of whatever's on the left, you're going to have to take ddx of whatever's on the right. There is no just write dy dx and then take the derivative. I have to take all the mixed up stuff on the left, all the mixed up stuff on the right, and just take ddx of both sides. That's step number 1. Step number 2. Collect all the terms. Uh-oh, that sounds scary. Collect all the pieces, all the terms that have a dy dx. So you have to look through. Probably simplify a little bit, probably multiply stuff out just a little bit. Collect all the terms that have dy dx on the left. Basically, simplify away anything that does not have a dy dx on it to the right. So what we're doing is instead of isolating y, because sometimes it's impossible, we solve for the derivative and then we isolate dy dx. So we're still isolating, just have to take a derivative first. And then we get dy dx alone, because he's our ultimate goal when we're finding a derivative. Isolate dy dx, leave him alone. And that's what steps 2, 3, and 4 are all talking about. If dy dx is in more than one place, we're going to have to go ahead and get all the dy dx terms on the left, all the rest on the right. If it's in multiple places, we're going to have to factor him out of the left and then solve for him to get him alone. I'm going to add one quick little note at the bottom. Note. This is going to be a little bit weird. You're not going to like it, and I apologize, but it's true. When reasonable. Wait, when reasonable. Get dy dx in terms of x. But I say when reasonable because sometimes, to be frank, it's impossible. So this is something we're going to have to be looking in the back of the book and say, hey, did they leave the derivatives in terms of x's and y's? Because I think I have to. Or, wait, I figured out a way to get it in terms of x's. When reasonable, there's one quick little note at the very end that says, hey, you have dy dx, sweet. Kind of like I did in the problem before. It had a y, it had an x. And I said, is there a way to make it match our other one? It had a y, it had an x. This was a correct form. But there was a way to get y by itself and then to plug in and go. This is actually kind of a silly one, because it would have been much easier to solve for y by itself. But remember, I'm preparing you for more mixed up functions. And I'm trying to say, even though you have an implicit derivative, sometimes you can make it explicit, which would probably be the preferred form. Okay. Let's do another example. So I can't just leave you today with just lots of notes and not much working out of the actual process. Okay, so find dy dx. We want to find the derivative. If it just says find the derivative, we assume it's the first derivative only, right? We never keep finding derivatives unless it states find the second, find the third, etc. Or it gives us a motion problem where it says find acceleration where we have to find the second. So find the derivative, find the first derivative. Get y alone. No. We already talked about him, that's going to be nasty. So what does implicit tell us to do? Take the derivative of both sides. Another reason why it's good to rewrite the problem in your homework, besides the fact you get points for rewriting problems and writing directions. If you have it written, then you can take dx of both sides, like I did. What do you guys want to do? Work our way from the left and just go for it, or work our way from the right and ease up to it? Go from the right. Okay, derivative of 10 is? Whew, got that one. Work left. Derivative of 5x is? 5, or technically 5 times x prime, which is 1. Hang in there. Derivative of, oh, they're both nasty. Well, maybe that wasn't the best thing ever. Can I take the derivative of y squared first, just to kind of help you guys with what's going on? What's the derivative of y squared? 2y. Oh, really? Yeah. Bring down the 2, make y to the 1. But, does y have his own derivative? Bring down the 2, keep the y. Bring down the 2, make it a 1, keep the inside the same. Times u prime, which is y prime, which is dy dx. Some people would actually put a y prime. If you look at the different videos online, some of them might like the y prime. I don't, because I can't tell if it's y to the first or if it's y prime, and then I get all confused. Or I don't write the prime very clearly, I think it's a y, and I just mess it up. You guys do you, though, if you want to go check out other tutors and see what they do from our online guys. But derivative of the outside, bring down the 2, make it a 1, keep the inside the same, times u prime. And what's the derivative of the inside? dy dx. Minus. Stink. I have a times, right? 3x times 1. We're going to have to somehow section off, splitting those variables up. Product rule. I'm going to write a minus and a parenthesis and do product rule. Second d first. Y times 3 is 3y. Plus first d second. 3x times. How do I take the derivative of y again? dy dx. It was just minus that part. It was just minus the 3xy derivative. Now, why on earth in my steps did I say get all the dy dx stuff to the left and all the non-dy dx stuff to the right? You see how I have two different pieces of dy dx, guys? I'm just rewriting it, not killing the seal. But if I need to get dy dx by itself, well, forget the 5, move him over, right? Forget the 3y, move him over, the negative 3y. I just want the stuff with dy dx to remain. Let's see if you can follow the algebra. To get rid of the 5, we have to subtract. To get rid of the 3y, we have to add. Does that make sense? Now, what was the next step? Just in case your mind doesn't automatically blare at you, I need to get dy dx out, so we need to pull out, factor. That's what the next step is, just to remind you. We need to get them alone. We need to isolate them. So the only way to do it is, hey, pull out that dy dx. He's stuck. Not equals him. Just factoring here. 2y minus 3x equals 3y minus 5. Last step, get him alone. And the only way I can see to get him alone is, that's a mess. Oh no, what if they asked us to like find a specific derivative at a specific point? Well, we would need an x, and what else would we need? We would need both, otherwise we can't plug in to get a number. But if they give us an x and a y, we'll be able to. Maybe we can get y by itself and plug, no, remember we looked at him. We're not getting y by itself. We're not even trying. That's ridiculous. This is not reasonable to go any further. It's unreasonable to go any further. We can't get y alone, so unless something looks vaguely familiar, exactly, no. There's no square down here. I can't substitute. I'm done. Okay. Implicit says derive right away. Derive as is. Whenever I have some sort of derivative of a y piece, I'm going to have to do times dy dx times dy dx, and then it's algebra to get them alone. We're going to end with, let's not do that. Let's end with one further example. I just want to see if you can start. You have a minute. I just want to see how you would start. What would you guys do? Get y alone, right? No. dx one side. dx the other side. Now what? Just go left. What's the derivative of 3x squared? Ah! Of x cubed. What's the derivative of y cubed? Woo! If you say times dy dx, you're kind of starting to get it. If you don't, you need to look at your notes and be kind of like, wait, what am I supposed to do again? And I'm not going to be able to finish because we're over. However, hopefully we can all at least kind of see what should come next. Yeah? Tomorrow we're practicing. Tomorrow we're asking ourselves the question, what is called the second derivative? Pretty much that. Bye, guys. Bye, guys. Stay awake, stay alive.
I'll try.
I know. Hang in
Clowns are
there.
gonna come for me this week.
What?
Clowns are coming